So the title of the talk when I put this together was called Cleaning BC, and this is a reference to the Clean BC strategy, and I think you're going to have a speakers talk about electrification and BC's goals in terms of cleaning or going beyond the clean state of our grid. I've been looking at that document a lot lately, so hence I put that word in the title, and I'm trying to talk today about the role, and I should have said our role, for wave supplied power. We don't know what all the roles of wave supplied power are going to be on our electrical grid, but we're going to go through the talk today, and I'll talk to you about the near-term function that wave power might have. Just to give me a bit of an idea, if I asked you to close your eyes, I won't make you do it, but if you did, and you imagined what a wind turbine looks like, can you just show of hands how many people feel comfortable envisioning what a wind turbine looks like? And you had Kern in here last week, so that everybody should have their hand up. Okay, so how many people, if I asked you the same thing, could envision what a wave energy converter looks like? Okay, so a few. John doesn't count. Okay, and upside type. Okay, so that's good. So the talk today, I'm an engineer. Rudyard Kipling has a connection to engineers. When we go through what's called a rite of passage when you become a professional engineer, they read you a sermon written by Rudyard Kipling about professional ethics. And so we're kind of professionally tied to him. But he wrote a lot of other things, and he wrote a collection of stories called the Just So stories. How many people have heard of the Just So stories? Even less than can envision what a wave energy converter looks like. They're called that because his daughter made him orate these stories to her when she went to bed, and he had to say them just so. And when he wrote them down, they became the Just So stories. So there's one called How the Elephant Got His Trunk. They're all origin stories, how fear came to the jungle, how this happened. It's all how things began. And there's a passage in this story that says, I keep 6 honest serving men. I'm sorry, ladies, it was like the early 1900s, and it was incredibly sexist. I keep 6 honest serving men. They taught me all I knew. Their names are what and why and when and how and where and who. And given that not many of us in here can envision what a wave energy converter looks like, I figured I would follow. This is called the maxim of the 5 W's and the 1 H. It all comes from a Rudyard Kipling story. It was actually a principle of journalism that they used to teach in university, and it was an axiom for investigations for police officers, detectives, the maxim of the 5 W's and the 1 H. Answer those questions. So it's a general talk. These are the types of questions I want to see if we can build answers in your own minds today. Who am I, for starters? Will lob a softball at me to begin with. If I get that one wrong, we're in trouble. What is wave energy? What's a wave energy converter, or a WEC? So I'm going to say WEC about 100 times. That's WEC, wave energy converter, and that's the industry term for the machine. How is WEC? Second time. Technology development being supported. So who's investing in this? What's the scale of the investment? Where is it happening? Where will WECs be deployed in BC? So I will be pretty local. I'm going to be a little bit myopic, and I'm going to talk about BC a lot. That's a research strategy for me. I feel like our jurisdiction is actually one that's a microcosm for conditions in the rest of the world, and if you can look at WEC development in BC and find roles and rationales, you can do it in other parts of the world. I don't believe in diffusing my limited mental capacity over Chile, BC, West Africa, et cetera, et cetera. How are researchers making WECs perform better? I'll give you a couple of examples on the technology of what we do today to solve problems that exist and how these machines work, just to give you a feel for what's happening. And who's going to lead WEC development in BC, Canada? That last question is really the conclusion of the whole talk. And maybe that'll be a surprise what my opinion to you is there, and that maybe it won't. Okay, so who am I? So I'm going to describe who I am in terms of the research I've done. And so prior to 2003, I was a PhD student, and I worked on cabled and towed ocean vehicles. So that picture at your top right, that is a autonomous, what we call a semi-submersible vehicle. It looks like a torpedo with a tall mast on it. So that's a diesel-breathing machine, and it swims around on its own, or radio-controlled. And that snorkel sticks out of the water surface, and it tows on a long cable, which I've just shown as a short cable right now, just to get it all on the screen, a towfish. And anybody take a guess what that system is used for? It's radio-controlled from a Navy frigate.
Submarine?
It's searching for something underwater, but not submarines. No, old things, nasty things. We don't use these anymore. Mines. It's a mine hunter. So you pilot the surface vehicle around, and it pulls the towfish, and you, from a frigate a long ways away, this thing will find a mine and give you a clear indication that it found a mine. So what I did was model the cables. The cable on that could be 200 to 300 meters long between the two bodies. And so trying to pull that fish where you want it to go when you're driving something at the surface around, it's kind of a complex problem. And so we use computer simulations to figure out how that system could be moved. And if you look at the figure at the bottom right, you can see at the top there's a circular path. That's that surface vehicle going in a circle. It's actually come into the screen and it's gone into a continuous turn. And the dark line at the bottom left is how that fish, as the surface vessel goes into a turn, the fish is losing speed and it's dropping, and that's the type of problem you have to deal with. Every time you turn around when you're towing something, what you're towing drops, and as you speed out of the turn, it picks back up. So this is a long-winded explanation to tell you that I'm a cable dynamics person by trade. That is my expertise. I work on cables, whether they're between vessels. The other thing we use cables for in the ocean is to moor technology. One more example, this is a remotely operated vehicle manipulator. So this is something you pilot off of a vessel. Again, this is usually used for science, and so this is loaded with thrusters. It's like a brick, it goes down the ocean, it can kind of move in all directions. But that yellow umbilical, when you're fully deployed, will be 500, 600 meters long. So this is like a small dachshund walking around with a 500 meter long tail, right? And the tail starts to dominate what the vehicle can do. So again, we use computer models and simulations to try out ideas on how to make the vehicle work, because it's not something you want to trial and error do in the field. All right, so a lot of simulating, a lot of computer models. And then in 2006, I met this crazy guy who had a wave energy company, and he's sitting down in front left. And this was John's technology. We'll talk more about this. This is called a point absorber, and the company was Wave Energy Systems. And for 4 years, I worked as an advisor for John's company, trying to figure out how this machine was actually going to operate. We'll talk more about what it does, but just to give you a sense of physical scale, the picture on the right, that is an average human being standing on top of it. So that is about the size of a wave energy converter. That's what you're looking at. And I think you saw wind turbines last week, so you're probably not in shock and awe at the size of some of this energy technology. And energy is a big, dirty business, and it takes mass and material to make power. And wave, just like wind, they both suffer from that same requirement. So I worked with John for 4 years, and I took all this stuff I was doing in cable dynamics, and we started looking at moorings. That was how I got pulled in. People thought I could look at the mooring and figure out how to moor this massive beast so that you didn't kill its power production, but you still kept it in one spot in the ocean. And instead of doing it by trial and error, we would do it using computer simulations, right? So I'm a modeling guy. So since 2012, I've been running a couple of labs on UVic campus. One is the West Coast Wave Initiative, and the other one is Primed. And we have a bit of a branding problem because we've got these two entities, and to give you an idea of what they do, whoops, sorry. Oh, we missed a slide, that's okay, go without. WCWI is my academic lab. So all my grad students, the work I do, pure curiosity-driven R&D. That's been going on for the last 8 years now, it's 2020, under that label. 3 years ago, I want to say 2 years ago, but we changed the calendar, so 3 years ago, we formed this Primed entity. And Primed is a merger of my team and the West Coast Wave Initiative, and you met Curran Crawford last week, and he probably told you he runs the Sustainable Systems Design Lab, or the SSDL, works on wind energy. We take those two groups, those two academic groups, and both of them are feeding tools and codes and people. So when they graduate, if we want to keep them around, we hire them into Primed, and we deal with communities directly, and we deal with companies directly. And the goal is to be able to respond to questions and requirements on timelines that kind of match with what the community and the company needs. Because when we work with grad students in WCWI or grad students in Curran's lab, they have theses, they TA, there are academic development objectives that, to be frank, the company probably just doesn't really care about. And so we kind of butt heads and mix. So Primed, I won't talk about it much today. If you have questions on it, there are a couple of community-driven projects that Primed is supporting that have just gotten rolling. Well, they're just being announced now, and so I don't have much detail in there on those. So, okay, so WCWI, this group I run, it's what we do wave-to-wire modeling. And that means we take computers and we try and figure out, in regards to wave energy, 3 things. We try and figure out what the gross resource in a region is. the net resource in that same region, and the usable resource in the same region. There are 3 tiers of resource. Gross means, what does nature give you? Like due to winds that John talked about blowing over the ocean, what waves manifest on the coast, how energetic are they, how powerful, how much energy is there to be had? So that's just what we call resource assessment. And we do that again using computer modeling and some field measurements and buoys. Net resource means if I put a device, a technology in there, and you saw an image of that yellow point absorber, this big thing, we haven't talked about how it works, how much can I get out? Like there's a finite bandwidth in terms of frequencies of waves and conditions that the machine will work. There are wave conditions where it won't work very well. So we have like a filter that technology puts on, but we can't get everything out that's there. What we can get out of the machine, we call that net. And so we use simulations to try and figure out in detail, like if we were to pick a spot off the coast and say, what happens when we put this machine in that spot every hour of an 8,760 hour year, except this is a leap year, so it's a little more than 8,760 hours, so we have a few more in there. So we want to build that profile. We want to know what the machine delivers. Now, what I hate about solar energy is people often cite the cost of energy on solar. In fact, have you had a solar talk yet?
Not yet.
Not yet. Tom will come in, right?
Right.
He's going to tell you like something between 5 and 8 cents a kilowatt hour. I guarantee it. Mark it down. He'll say it. It'll be in there. I don't like it because renewable technology depends on where you put it. If you go to a place where it's always dark, you would pay for the solar technology, and how much power would you get? You'd get next to nothing. And so the cost of every unit of energy that you got is very high. So you can't cite costs of energy on a renewable technology unless you know what the resource is and where you're putting it. And not only what will the device give you, that's net energy, but will you be able to use it? Because if you add the renewable technology onto a system that already has other sources of generation, you're not just going to board them up and throw them away. Those are assets. You have a capital investment tied up in a diesel generator, let's say. You can't just garbage it. So the renewable power has to merge in or integrate into that system, and it has to displace diesel generation in a productive way. So for example, you can't take diesel generators and turn them on and off and on and off and on and off and on and off. You'll ruin the generator. It will start consuming a liter of oil a day, right? Just from being all this ramp up, ramp down activity. And so if I was to bring in a renewable that required me to ramp up, ramp down the generator, on, off, on, off, on, off, I would have new costs come in that I never had in the first place, and those new costs are associated with the renewable. So integration, or finding out how much of the net resource is actually usable, is a really difficult problem. So we try and work in all 3 areas, and we try and do that using numerical models wherever we can. And there's the slide I was looking for on the 2 labs that got moved. So, okay. All right. Before we really get rolling, I'm doing the classic mistake of having too long an introduction, but before we really get rolling, I want to make one thing clear. Wave energy is not a new idea. I actually hate the phrase wave energy. In fact, in the industry, we call it marine hydrokinetic power. Wave energy, or marine hydrokinetic power. You get the idea. Wave energy is often associated with some kind of technical voodoo. Like it just sounds like a buzzword. It almost sounds like Rube Goldberg if you say it enough. Marine hydrokinetic, there's nothing new about making power from moving water. Right? We have done this forever. Well, not forever, but a long time. Waves are just a different flow pattern of water. A tidal current you can envision goes from here to there, and it kind of has a uniform flow. It might be stratified over the depth of the water column, but it's moving in one direction. As we'll talk about in a second, waves are just a cyclical orbit of water. It's a gigantic sloshing action going back and forth on a distance that's really about from that wall to that wall, or a little shorter, and it's occurring on a period of 13 seconds. And you're trying to stick something in that oscillating flow, water moving over there, turning around, coming back to that wall, coming back to this one in 13 seconds. You want to put something in there that'll capture that kinetic energy. And it's been tried for a long time. So one of my favorite authors, Jules Verne, he wrote, and I changed this one, so anything one person can imagine, other people can make real. And that's what wave energy is about. People have envisioned this for a long time, and we still have people today trying to make those old ideas real. Materials, corrosion, mooring dynamics, control, integration, project economics, all these things we got to wrap bows on and tie up these problems So old ideas can become useful. So if you went to that website that's at the bottom there, PLAMISWave.com, PLAMIS doesn't exist anymore. We'll talk about that in a second too. In fact, if you type in that web address, what you're going to get is a solar technology webpage. I kid you not. Somebody just took the domain and brought it over. But on the webpage in the past, it used to say that PLAMIS was the manufacturer of a unique system to generate renewable electricity from ocean waves. PLAMIS is like a sea snake, so the idea at the top left there is you can see at the very top the wave is coming from left to right, and you have these articulated cylinders, so left to right or left comes. So the wave's coming from there to here, and the lead cylinder will be this forearm, and it's pinned to another cylinder. And as the wave comes by, the cylinder rises up, and then this one goes up, and we ride over the top of the wave crest, and off that wave crest goes. Next wave crest comes by, we ride over it. And if you focus on the joint, what you're getting is a relative rotation. And as soon as you have relative motion, you have the capacity to generate power. That's what electrical generators do. They typically use a gasoline engine to make constant rotation, that's relative motion of a rotor relative to the base of the machine, use the rotation to make power. Wave is a little more difficult because you have an oscillating motion, but you can still take that rotation, that relative movement, and use it to drive hydraulics. You can charge hydraulic cylinders and accumulators and take the charged hydraulic fluid and then run motors and generate electricity. So this is a sea snake. It's unique. This was, I think, 2010. You have to turn your head sideways, but on your left, this is a patent from 1912. And this is a wooden PLAMIS. This is exactly PLAMIS, right? It is over 100 years old. It was invented a long time ago. Every patent PLAMIS had for the basic idea is invalid. Patents on the hydraulics and the inner gearing and how they're taking that relative motion and turning it into a hydraulic system, that's valid. That's IP. This is old. So the central wooden piece there is the main house where the powerhouse is, and you have these two outriggers. And so the middle wooden piece is where my fists are coming together. The outer wooden pieces are where my elbows are. When the wave comes by, the system just walks over the wave and you get relative rotation. This is Marvin's wave motor, and this was filed in 1922. And I had one that was filed in 1785, and I can't find the darn piece of paper anymore. I was going to put it in. But so how this works is that you have something called a stator, which is this. Can you guys see the mouse when I move? So that's a stator, and it's rigidly connected to this vertical piece, and this cage on the outside are all part of that one piece. The little cylinder here is the float, and it's allowed to slide on that central column. And when that float slides on that central column, you have a relative stroke, and he was doing something with that stroke to generate power. He has mechanical work, and he can do something with it. Today we would make electricity. I don't know what he was doing in 1922. So these are daisy chained. So he's got two units that are connected by a mooring line. He's got a surface float over here that's maintaining a vertical orientation of this main anchor line coming down to the two anchor points. And so those two surface floats, they're very buoyant. They want to stay on the surface of the ocean. And if they start to come together, they'll go into the water. Buoyancy will push them back out. So they're actually keeping everything drawn out, keeping them away from each other is the idea. So as the wave goes by, that plate down there sits in relatively quiescent or still fluid. The floater is moving up and down with the wave. And can everybody kind of see how we would get relative motion? 1922. This is Ocean Power Technologies. They built this device and were going to deploy it in 2006, and 2008, and they went bankrupt one day before it went into the water. So this yellow piece that you see right here is not fixed to that yellow cylinder. That's just there for navigation purposes. Yellow is a universal warning color, meaning stay away. And so that central column is this yellow tracing all the way down through the black. That is a rigid body. And it is connected to this plate that's sitting down low in relatively still water. And then the yellow piece rides up and down when the wave goes by. And this superstructure up here is connected to a hydraulic ram, which goes down and it goes into a hydraulic cylinder. And so as the yellow piece goes up and down over that central spar, we call it, we pressurize hydraulic fluid, and they go and use that to generate electricity. So it's the exact same idea. So it's extremely old. There is nothing novel about any of these architectures or concepts. So. Okay. All right, so what's a wave? So 4 images of a wave. With wave energy, we are not talking about the top left. And if you were to think about the power in a wave, what's the best demonstration of the power in a wave? It's when it breaks. Because when it breaks, one, it's near shore, where most of us are standing, and we can actually see it, right? We don't usually go and sit in a boat about 8 kilometers offshore unless you're involved in the fishing industry or you're a pilot or something like that. So that's what we see. At that point, the wave energy is lost. It's gone. The resource wasn't harnessed and it dissipated itself on the shore. So it's a lost cause. We're also not dealing often with the situations in the bottom 2 pictures. Those are what we call very clean, very regular seas. So what you're seeing is that the wave crests are almost parallel to one another, and the waves propagate. So if the wave crest stretches across like this, the wave is going perpendicular to the crest line. And what we see is the crests are uniformly spaced, meaning we have a uniform wavelength. If you were to stand and watch the waves arrive and you were to count the time between wave crests, it would be very regular, be the same time, same interval all the time. There's another situation on the bottom right that's a very regular sea. We're also not really the top right, which is called a witch's cauldron. And that is a mixed sea where you have waves coming from all directions. And it's really hard to discern even where the wave crests are. If you look close, you can kind of see them. We're kind of in between the top right and the bottom right. If you combine those 2 pictures, that would be a typical operating condition. And we're offshore. So I've cobbled together some different slides from different talks just to give you an idea. So the main things here, we're not in the surf zone that's at your right-hand side. We're not on the beach. We're out in a depth of water where the swell is relatively unaltered. And swell refers to basically a coalescence of wind waves that you would see on a lake. If the wind is to keep blowing for hours and hours and hours over miles and miles and miles, which are conditions that don't usually develop on a lake where you would go and have your recreational activities, and you see wind waves there. But on the ocean, those wind waves coalesce and they form very long wavelength waves. So the distance between those crests that you see on that white line will be over 100 meters. And the time between those crests, if you were to stand and watch the waves arrive, will be around 10 seconds. These are great, big, slow moving entities with a huge amount of kinetic energy because of the mass of the fluid that's cycling around inside the wave. Okay, the direction of travel is basically what you would see if you were to watch a crest. The crest will appear to move. The thing about a wave is that there's actually no mass transport. I don't know how many people are wave experts in here. This is just a little bit of background. What you see when you look at a wave is that the nominal water line, if it was a flat sea, you'd have a level line right going through the top of this nice linear wave that I've drawn. And I'm going to put my pointer right on a water particle. And what happens in a water wave is near the surface, that particle of water, instead of being where it wants to be, it's basically going through an elliptical orbit. And the particle to its side, so the particle to its right, is going through the same elliptical orbit, but they're phase shifted. So when this particle is at the top of its cycle, this particle is at the bottom of its cycle. And we could draw a particle in the middle, and I could draw that circle, and where that particle is going to be is sitting on the point where my pointer is. So what you have is all these particles that are a little bit out of phase, and if you freeze frame like this, and you trace a line through all those neighboring particles, what you form is that wave profile. And that's what you see. And when you watch the wave, because of this motion, if as human beings, when we sit from a stationary reference and we watch a particle that's on the top of the wave, because we don't really resolve the individual particles, what would appear to be happening to us is that this point on the free surface would appear to move to the right. And it would look like it's moving. But what's happening is it's just the profile is getting picked up by the next orbit. So the particles are only going through these elliptical orbits, and those orbits are only like 10 to 12 meters wide. So that's what's occurring in a wave. As you go down in the water column, the wave actually has an impact. And if we had a wavelength of L, let's call it 100 meters to be convenient, you'd have to go down about 50 meters to not be experiencing any of this circulation. So it goes down quite deep. And if you've ever swum under a wave at a beach, if you've ever gone down and dove underneath, or if you were lying down the bottom at a wave pool and a wave goes over the top of you, you would have felt yourself get sucked up. You would have been pulled up off the bottom, because when you have water that's going through an oscillations, there's always changes in velocity. We're moving up, we're moving down. And if you're changing velocity, you must be accelerating. And for anything with mass, and water is heavy to accelerate, you must exert what on it? To make something accelerate, Newton's second law says you have to hit it with a force. And so if those particles are having those oscillations, I could go down, 20 meters, 30 meters under the wave surface. The particles are accelerating up and down. There is a force that is oscillating up and down. There's a pressure change. There's a pressure oscillation beneath the wave. So when you work with a wave, you could work with the moving water. That would be like putting a turbine in the middle of this sloshing pattern. You could put a buoyant body at the free surface, and you could use Archimedes' principle. So as the water goes up, if you were to try and hold something steady and the water climbs around it, you would feel buoyancy trying to lift it out of your hands. You could work with that phenomenon. Or you could work with the oscillating pressure beneath the free surface. So these are the different ways you can work with a wave. It's not like the wind industry, easy, where the wind is blowing and you are going to engage with the kinetic energy of the wind. You have one choice, right? That's it. Here you could work with buoyancy, you could work with an oscillating, sloshing velocity, or you could work with an oscillating pressure. And what do you think this does to the design space of wave energy converters in terms of the number of different concepts out there? It goes boom. And that's a problem, because now you have a limited number of people in the world working on a population of technologies, and they're not even close to being the same. And that's why it's taken 100 years to even start advancing some of these things to this point. Boy, it's a good thing we have 2 hours. Sorry, trying to pick it up. Okay, so swell, there is a difference between waves and swell. Just when you go out in the world and you said you were at this talk, one thing you could take away, waves refers to like local winds. You go to a lake, you see waves. If you go to Tofino, how many people have been whale watching off Tofino? You clueless? Okay, and you probably got out far enough, you got outside the Broken Islands, I'm okay, my wife gets it really bad, it is where you start going up and down on that 10-second period, and it's like 12 feet up, 13 feet down, 12, that's swell. And swell forms, just a little example down at the bottom, dependent on the wind speed, and dependent on the distance. So here I've said that the fetch, or the distance the wind is blowing over in a correlated manner, it's 50 nautical miles or 90 kilometers. So like not a lake in BC, right? You need space for this to happen. And the wind was blowing for 6 hours. So I fixed the distance and the time, and if you play with the wave speed over the distance and that time, 15 knot winds give you 1.5 meter waves, 25 knot winds give you 3 meter waves, 40 knot winds give you 5 meter waves. That's 15 feet. And when we talk about waves, it's peak to trough, right? So it's from the bottom of the trough to the peak of the crest, or 2 times the amplitude. Okay. A lot of words here, but the main point is that as waves approach shore, I talked about that circulation pattern. See if anybody's listening. If it's 100 meter wavelength, the circulation pattern goes down to about 50 meters. Okay, so that wave's coming in from really deep water. I'm moving out of your camera view. And it starts to hit water, it starts to hit depth of 50 meters. The particles at the bottom that are moving start to do what to the bottom? They start to rub. And as soon as they rub, there's friction. As soon as there's friction, there's a dissipation of energy. And the wave starts to die, right? And the physical view of a wave dying is it starts to slow down. So the apparent speed, we talked about how there's no mass transport, but the crest looks like it's moving with the speed. And these speeds are actually quite high, right? But it starts to slow. And so when a wave comes in, you could have a parallel wave crest. But if this area is shallower water, this part of the crest starts to slow down before this part. And so this part slows and drags, and this one keeps going, and the whole wave crest starts to turn. So as waves in deep water start to come to the BC coast, the bathymetry of our coastline starts to steer and focus the waves. And this is where now, if you imagine having one wave crest, coming from one direction, but there's another wave in the sea and it comes from another direction. And all these things come to the shore and they refract, this is called refraction differently. You can bring these things together and create local hotspots. So we don't have to go all the way offshore if we can find a nice sweet spot where those waves coalesce and get more power at one site. The part down here, this C is called celerity. It's basically the speed of the wave. So this is the apparent speed if you watch it go. So this would be in meters per second. So if in deep water, if you have a wave of 10-second period, it's going to look like it's moving at 15.6 meters per second. 1 second, 16 meters. That's how fast the thing appears to be moving as it crosses. As you get to shallower water, and this means now this relationship disappears and this one takes over. That's a square root of depth. And the depth here, I'm looking really shallow. So this is wavelength over 20. So if it's a 100-meter long wave, we're looking at water that is 5 meters deep, which is, you know, if you go to the beach and you start walking, it takes a while to walk out before you get to 5 meters deep. We have some areas where we have a very shallow shoreline. So it drops down quite a bit. So we'd be looking at the square root of 5. This is a bad example. 2.3 times 3. So we'd be looking at 2.3 times 3. Let's just call it 3 times. Let's call it 9. So we go from a wave that wanted to be working at 16 meters per second. It gets into shallow water where it's only going 9 meters per second. And this is why waves break. So in the top of the wave column, the wave wants to be moving at 16 meters per second, but the depth is holding it back. The whole thing can only advance at 9, and the top starts to fall over, and we break, and the wave is lost, and no energy was gained. So, how are we doing so far? Everybody okay?
Could I ask a question, please?
Just one, yep.
Yeah. And where does the word swell come into what you just described?
So that would be an effect on the swell. So the swell is a clean wave, but it's a water wave with a egregious wavelength and a very long period. And it's basically formed from what you would envision as being a regular wave on a lake. So it's a collection of energy from different waves that come together to make something big. It's like one monster ingesting a bunch of smaller monsters and just starting to swell up. All the waves get absorbed into one entity. So, okay, so I'm going to try and get across what a spectrum is. So in engineering, if we're going to design machines that work in the ocean, we have to know what all the components in the sea are. And so the picture on your right, the red line, that's called a wave spectrum. And it's basically just a visual accounting. It's a balance sheet of wave energy. The vertical axis means bigger wave, all right? The bottom axis, the horizontal one, is frequency, or 1 over period. So if we look at a frequency of 0.1 hertz, we invert that, that's a 10-second period wave. If we go out here to 0.25, that's a 4-second period wave. So you can see in the ocean, the red line is telling you that there's more power, meaning there's bigger individual waves. This is a collection of waves, all existing at one spot at the same time. And it's basically telling you what those distributions look like. So each one of these things, to go to your question, let's call it one piece of swell, like one wave with a crest and it's moving in a direction. That's one layer. This is another piece or another instance of swell, and another one, and another one. And they're all coming from different directions, they all have different periods, and they all have different heights. If you bring them all together, that's what the engineer designs the wave energy converter works with. Simultaneously bring those surfaces into one shape, that's what you have to work off of. It's very powerful, it's very noisy. It's not a clean input to a machine. And what you're seeing here is I've just tried to color code the different pieces of the overall sea. We call this an irregular sea because it looks irregular, but it has many regular components to it. And so each of those waves is, the blue one here is this band. So this section of the red line defines, if I go down, it would tell me the frequency of that wave, and the height of that red line would tell me the height of that wave, sorry. So that's a spectrum. Now, this is a directional spectra. So if you could, what we've added here is a direction axis. So here's the frequency axis, and I'm going to go back up. So this vertical axis where it was power, in this view, that axis is coming out of the page at you. And so where you see dark colors, what we've got here is a surface, like a sheet that's billowing up. And the dark color is telling you that you're at a peak on that surface. And how that surface changes as we move up and down is telling us how, at a given frequency, if I just move up and down here, how the energy is distributed over different directions. Because all that power is coming something from here, something from here, something from here. So there's a directional spread to waves as well. So this is a little harder to interpret. This we call a non-directional spectra. This one we call a directional spectra. So the last two things, I want you to know or leave knowing what energy period is and significant wave height is. So significant wave height, or HS, is basically calculated from the area under that curve. And it shouldn't be a big surprise that if that curve, if I take and stretch it up, and I have more area under that curve, That means the curve is at higher points on that plot everywhere. We have more energy. And the area underneath that curve magically, well, not magically, but it reflects the average wave height. So if you were to stand and watch waves go by, you watch peak to trough events, and if you were to observe them and say there's a 5-meter wave, peak trough, and then you wait 2 seconds or 5 seconds, and then you have another peak and a trough, and that one was 2 meters. And you log that down. Next one was 6, then 8, then 10. If you were to do this all day, and then take the average of the top third of all those recordings, that is actually defined as the significant wave height. It's the average of the top third of all wave events. And it's magically related mathematically to the area under that spectrum. It's kind of a beautiful thing. Energy period is basically the average location of all that area. So what some people call mean frequency, if you were to go and find the centroid of this shape, the center of mass of this area, it would be somewhere right about here, and that would be above what's called the mean frequency. If I take that frequency and invert it, I get the energy period. So it's basically the average time between wave crests. So this is a wave record. So the red line here is time going by, and the waves are going up and down. And what you see, these are individual waves. So from that peak to that trough, that's a wave, and it has a height. This is a peak to a trough, that's another height. So when you bring all these regular pieces together, you get this irregular mess, and so waves become individual things. And then H max, this is what you call a road wave, like this, and this happens. Unfortunately, it's happened off our coast a couple times here with dramatic consequence. And the HS that we're talking about is also called H1/3. It's basically, I've just kind of indicated it graphically, it's an average wave height. So as engineers, we work with HS and TE, energy period and significant wave height. Wave energy, last thing I'm going to throw that looks mathematical. So if you can imagine, here's a wave going by. Imagine going down to this depth, and we got a little particle that's sitting right here. And that particle is oscillating around because it's part of this whole wave circulation. And there's an oscillating pressure on that particle. So what wave energy is, the red line here is a screen door that's dropped into the ocean. It's 1 meter wide. It goes from the seabed all the way up to the sea surface. And what we're looking at are all the particles of water that sit on that screen door. And if we have an oscillating pressure, that's a force being applied to an oscillating velocity, force times velocity in mechanics is power. And so over time, if we track the power that the particles on this side of the line are applying to the particles on that side, we can track it over time, and we take an average. And when you average that out, you're left with a number, and that number is the wave energy. And it's something that occurs from the seabed to the sea surface. It's a total of what's occurring all the way from the bottom all the way to the top. And that's what wave energy is. Okay, so for a regular wave, there's mathematical expressions. So we use J to represent it. There's mathematical expressions that tell you what that is. Now this is not what we find in the real world. This is what we find. We get these irregular conditions, and in irregular conditions, you have many of these waves inside this. And so the wave energy or the wave energy transport is not the same, and so it's a different equation. Now to make this easy, if you take the density of water, you take the acceleration to gravity, you take 64, and you take pi, if you put this all together, you basically get 500. It's 496.78 something or other. It's almost 500. So if you take the significant wave height, and this is in watts per meter, so if you want kilowatts per meter, which engineers do, we take the 500 and we make it 0.5. So if you take the significant wave height and you square it, and then you take the energy period or the average period, if you take that product and divide it by 2, that's your wave energy transport. So on our coast, you know, if we have a 2 meter wave, that's very, very common. A 2 meter wave on our coast usually occurs at about 8-second period. Let's do the math. So 2 squared is 4, multiplied by 8 on a good day gives us 32. Multiplied by 0.5 would take us down to 16. 16 kilowatts per meter, right? So on a 1 meter wide screen door, you got 16 kilowatts of energy transfer. And in the modern world, a household that you or I live in, our peak demand would be 2 kilowatts, right? So we got 8 houses on a 1 meter section of water. That's gross. The question is, how much energy can you get out of it? So. All right, so all this is saying here is that if you look In the summer, on a clear day, you'll have 1 kilowatt on 1 square meter of ocean. On that same square meter, you'll have about, on our calmest calm day, you're going to have about 10 kilowatts going through that. So you got 1 kilowatt from the sun coming down on the ocean, and going through that same square patch, you got 10 kilowatts from a wave. And in the winter, we go way, way up, obviously. So it's very powerful. There's a few slides in here I'm going to skip, but these are, now we'll look at machines. What's a wave energy converter? So I've talked about Polamis up at the top here. This is called Wave Dragon. This is an overtopping device. So basically, this thing sits on the surface of the ocean with great big arms, and the wave gets channeled in. It gets run up over a ramp, which is sitting right here. The water runs up and it falls through, and sitting right in that exit duct is a Wells turbine or an impulse turbine. Water falls down, and basically at this point, this is a hydroelectric facility, right? This is the reservoir, it's funneling down through, and you make power. A point absorber is basically a device that's bobbing in the ocean, and it's going to pull on a PTO, and then we have these terminators or flap devices. I'll skip that one. Oscillating water columns. So this is an example of one here. This is a shore-based one. So as the wave comes in, it basically funnels up a structure, and the water surface is sitting inside, and it pushes on air that's trapped in that chamber. And so when the wave comes in and rolls up, pushes on the air, it pushes it through a duct, and it goes through a turbine. And you can hear these devices, because when the wave rolls in, what you hear is the system exhausts, it breathes out. And when the wave goes down, we draw a low pressure in here, and what does the system do? And people don't like them, but amplify that by whatever. So these are air breathers. That's Wave Dragon again, just an overtopping device. This is an oscillating flap. I think the picture at the bottom right gives you the idea. This is called a wave surge device. So the flap is mounted on the seabed, pretty shallow water. That yellow piece at the top you would actually see, it would break through the surface. And as the wave goes by, that flap wants to keep going up and down, and we get down here relative rotation, and we make electricity. Polamis again, so this is where the value in Polamis is that at all the joints, you can see there's all these hydraulic cylinders that are basically compressing and pushing hydraulic fluid. When those cylinders move, they charge a tank and they make electricity. This is the point absorber. This is CETO. This is an Australian one. And basically what you're looking at here is CETO 5 and CETO 6. And this is a float. It sits in the ocean. The wave goes by, goes up and down, pulls on a string. And when it pulls on the string, it pumps water. And from CETO 5 to 6, they move the pump from being at the seabed to being at the top. Like, these are changes in the engineering of these devices that are still going on today. They did that to make it easier to service. So. This is that OPT one. This is another point absorber. I mean, basically, again, you've got that central piece. It's floating. You've got the outer pieces floating as well. These two things are bobbing in the ocean, and if they bob differently, you get a stroke and you can generate power. Terrible resolution. Purple indicates the technology and development. This is as of 2016. So you can see there's a concentration in Europe. The red is facilities. So those are field test facilities or large tank tests. Programs that support it. Marinette was the 7th framework program for research. It's a terrible name when you convert it to English anyway. It's an EU-wide program, and they were actually funding like 14 different test centers that were in the UK. This is just to coordinate test centers and to have companies be able to go from site to site where they might be able to do different tests at different sites, and they would fund that movement of technology. So I don't know what's happening with this now. They're not going to take EU funds into the UK to subsidize that. Just an example of a technology called WaveStar that was built in Marinette. I'm going to skip that one. That's DT Ocean. So in terms of what test sites for these devices look like, this is the Cornwall Wave Hub, which is in the south, it's in Cornwall. And this is basically, field test sites up here. You can see how this is a licensed area. It's that's a 6-mile limit, not nautical miles, 6-mile limit. So let's say 10K offshore, and they're grid connected usually. They usually have transformers and interconnections here. And governments usually pay for the infrastructure to the shore, and then the WECs come in and they pay for their interconnection, and they lease space. And that lease goes into supporting the test center. So there's a number of these in the world. That's Cornwall. This one will be fun to go to. This is in Oahu. This is a Marine base on the north coast of Oahu. The Americans are a little different because the US Navy has something called the net zero mandate, which means that their military bases have to have net zero, it's not emissions, it's imports. They have to be able to run the base by themselves. And this is a wartime thing, I believe. And so wave energy is something they're looking at Oahu. So the US Navy actually funds quite a bit of technology development at this one. Same idea though, 6 kilometers offshore. This is a little closer actually. And then you have bursts and interconnections. This one's in Oregon. And this one is just being built. This is the Pacific Marine Energy Center. And there's 2 parts of the Marine Energy Center. They have a North Energy test site and a South Energy test site. And what you're looking at here is a schematic of the South test site, which is grid connected. This is being built right now. I grabbed a slide from a colleague, and I don't want to go through the whole thing. This is the history of how this PMEC facility, which is at Oregon State University, got created. I guess the things I wanted to point out is that this is all Department of Energy funded in the US. So the US DOE considers wave energy converters to be the same as hydroelectric. They're all water power. And this money is still flowing into Oregon State University, even though you know who is sitting at the head of the US Department of Energy. And to be honest, I think it's because he has no idea that he's funding wave energy research when they allow the water power program in the US Department of Energy to invest in this stuff. Because it's all it could be a hydroelectric facility at the top levels of the administration. So really strategic move by the marine people way back to get that done. So the funding here, $35 million to develop this test site, that actually has been increased. So since 2009, there's been $108 million going from the US Department of Energy. 66 million of that went into Oregon State University alone. So to give you an idea, my program is probably, and I don't say this to be bragging, just to illustrate the state of affairs, like our program is probably the flagship program in Canada for wave energy. I think our investment to this point is about 4.4 million total Canadian. It's like $2 American. So the scale is quite different. The DOE also invests in technologies. So there's been 21 million into companies. I've given you some images of some of those things that they've pumped in between 2008 and 2014. There's been more since then. They also ran a thing called the Wave Energy Prize, which was literally a come one, come all. Show us your craziest wave energy conversion inventions, and they ran a competition through stages to whittle them down, and they put them through tank testing and paid for all the experimentation with just novice inventors, right? Just to see if they could get an idea by opening the net that kind of changed the performance level of the technology. OWED is the Oregon Wave Energy Trust. So I told you about Oregon State University. Oregon, the state, took lottery proceeds and started funneling them into wave energy research in 2008. So they've put in $6 million into different R&D projects by themselves. So the state of Oregon has outfunded, the country of Canada when it comes to West Coast wave energy research. So, and just to give you an idea of the Canadian picture, sorry, John, I had to do it. So Sync Wave Energy Systems, which was John's child's and just corporate child from 2006 to 2012. So between 2008 and 2010, it was very successful. Sustainable Development Technology Canada, 2.7 million. The BC Innovative Clean Energy Fund, 2 million. And NRCan put in 4.6. And not 1 cent of that money was ever accessed or used because in Canada, they put private equity sharing conditions on it. So they wouldn't give a pure public subsidy. So that doesn't exist in the US. The DOE money they can spend. There are other conditions. They have to share what the knowledge they generate. But in Canada, you can't even get to the sharing knowledge point unless you have an investor. And if you go back in the financial history of the world, that was a very bad time to be getting money and then be required to go get angel investors because nobody was investing in wave energy technology at that time. So. Okay, so I'm a modeler, computer, and John, you want to break at 11? Okay, yeah, okay, all right. So we'll have a little bit of talking after 11, but we'll be all right. Okay, so why model? I've shown you pictures of actual devices. People have made steel, they've put them in the water. The US DOE is funding everybody. This is WaveBob. This is a point absorber. So just like that OPT one, there's the central spar, there's that annular ring on the outside, 2-body point absorber, they're bobbing in the water, making relative stroke, generating electricity. So 2001, they did sea trials way back in 2006, there's the picture. They were accepted at a grant to go to the Cornwall Wave Hub. They were going to deploy there and prove on a grid-connected scheme how they could generate power. They were the Innovation Company of the Year from Engineers Ireland. Lockheed Martin signed an agreement with them, which was a really good thing to be doing back pre-2010. They got 2.4 million from the US Department of Energy. There's the US DOE again. I mean, money is falling from the sky out of the US Department of Energy. And then in 2013, just ended. And it ended really fast. They were supposed to be a partner of my program, and I got a call one day saying, we might want to tear up that agreement. And basically what happened is, I've underlined it here, they couldn't find a long-term investor. This is what happens in wave energy with technology push. It's look what I can do, look what I can do, look what I can do, look what I can do. And nobody cares, because what you can do today is generate power at a price that is economically unviable, right? You just haven't learned enough to get the technology to a point where it's competitive with hydro or solar. And so nobody would invest. They have no market. They have no future market that they can point to. At some point, it falls apart. And this has happened with one company after another. This is the valley of death. And I'm sorry, John, I put the sync wave device on one side of the valley of death. And it never went to the other side. And again, this has happened over and over. And so demonstrations are good for technology readiness. They are not good for technology performance. You do not want to build an 80-ton machine that has to be deployed in the ocean using a vessel that will cost you $100,000 a day to do the deployment to iterate your idea. You need to do that well in advance of going to that point. And for whatever reason, the sector in the 2000s thought, we will do this, we will build it, deploy it, because there is nothing new about making power from moving water. And that proved to be an absolutely near fatal decision for the entire sector. So as of, I would say, 2013, 2012, there has been a reset. And I'm going to show you this, and this might be a good place. We'll do this, and then I can break.
A $7 million wave energy generator that sank off the coast of Carrigalinga has been blamed and slammed as a waste of taxpayers' money. Half the project was funded by government grants. Now fears have surfaced that it may never reach its destination.
This is pretty much how the green wave generator is supposed to look in the water. Problem is, it's meant to be off the coast of Port Macdonald, not Carrigalinga.
Not surprised at all. There's certainly a disaster waiting to happen.
It started sinking on Sunday when some of the airbags burst. The company that built it, Ocean Links, is deciding whether to salvage it, but Brett Devine says it'd be cheaper to destroy it and start again.
There is a chance it could be raised and utilised again, but it'd be quite an expensive exercise.
The previous federal government promised Ocean Links more than $4 million to develop the technology, despite 2 failed attempts in New South Wales.
That's the US dollar.
It received most of the funding, but needs to reach certain milestones to get the rest.
Mr Devine says the generator should have been towed to Port Macdonald on a barge like the one that carried the Sydney Adelaide Clipper home from Scotland. He says it would have been more expensive, but at least it would have got there.
They took a cheap avenue here and they've come unstuck very, very quickly.
Ocean Links plans to sit the generator 4 k's off Port Macdonald and connect it to the grid. The local council raised concerns months ago.
We did wonder how they were going to transport it. We thought initially they may try to construct it on site.
Mark Mooney, 7 New.
Okay. So I've got a couple things here, and then we'll leave it there. So a few common themes, and this is repeated over and over. Not enough budget. So it was $4 million US. Like, do you know what it costs to make Site C? Like, this is proven technology. We have built hydroelectric facilities many times. It's much more than that. So new energy technology, mainstream society, we've had first world problems now for about 30 years. People are not willing to publicly subsidize this stuff. And so wave energy companies try to do this on the cheap, but they try to do field testing on the cheap. And this is what happens. And every time that happens, and it happened in Oregon too, with a project with the Macaw First Nation, a company called Finnevera, who used to have an office in Vancouver. They had a converter sink, and when it sank, it went down, and then a storm came through, took a big long point absorber converter, which is now sitting on the ground like a log, and it dragged it. And what do waves do? Do they move in one direction, or do they go back and forth? They go back and forth. And it took the thing and picked it up, and it dragged it through the crab or lobster, something that's valuable on the bottom. And it pulled it through, and after it pulled it through once, the waves turned around and pulled it right back through again. And this went on for about 48 hours, right? And it took a long time. That was 2001. The Oregon Wave Energy Trust wasn't able to start putting money back into wave energy for another like 8 years, right, before that fixed. The other thing with Australia is they have a panic mode because on the west coast they do have a generation deficit, and they like in the area of Perth, And it's a kind of a fractured country in terms of the grid. So they have a motivation for renewables on the west side. I'm going to show you this, and then we'll break here in just a couple minutes. This is the 2004 Integrated Energy Plan from BC Hydro. And the column at your left is 2004. You're going out to 2018. I know it's small to read. And those bars are showing you the supply stacks. So the black are the modern AC connections between the island, this is Vancouver Island, and the mainland. So the black is power coming to us from the mainland. The gray, the hash mark one you see here, this is an old high voltage DC connection, which is down near Duncan, and it was getting phased out in 2007. So that capacity, this is power you're looking at, this is capacity chart, that disappears. And the gray here is existing IPP. So these are private sector companies feeding power into the grid. The white is what was going to come starting in 2008. Don't forget this is 2004. That was going to come from the call for technologies. They wanted 150 megawatts of new supply. So hey, you're out there, give us your ideas. We'll sign a contract with you. We can take up to 150 megawatts of input. And the black lines are two projections on Vancouver Island demand. So if you're sitting in BC Hydro in 2004 and you're looking at that curve, you're thinking, oh my gosh, we have a problem. Now in 2009, they ended up spending $230 million to put 600 megawatts of capacity on a new cable that comes from the mainland to Vancouver Island. We all use power that comes off of that now. So that ended up happening right here. All right, they committed to $230 million to put another cable under the Strait of Georgia. But in 2004, they were thinking, we got an issue. And they knew about this before 2004. And what you might not know is that in 2001, British Columbia was going to be the site of the world's first grid-connected wave energy demonstration plant. And it was motivated by that forecast shortfall. So there's a panic factor with all energy supply, right? There's a bit of a panic. We got to do something drastic. And so they put out a call for proposals. And they asked wave energy companies to come in and put in, we were looking for 4 megawatts, and they were going to grow it to 20 megawatts to cut into this 3 megawatt shortfall that they were looking at. This is the document. I didn't know this existed until a few years ago. And if you look at the bottom, this is the timeline in their proposal. So in November 2001, they were going to select the company they were going to form a JV or a joint venture with. Then what they were going to do is they're going to do 8 months of resource assessment. That's a joke because the international standard now says you have to do a minimum of a year. But this is 2001, so those standards didn't exist yet. You were going to design the converter over 4 months. Laughable. You were going to build it in 6. Laughable. And then you were going to generate power for 20 years, right? First of its kind. Like, you can call this ambitious, you can call it other things as well. But this is what happens when fear creeps into the equation. We get a lot more tolerant all of a sudden about this investment. But then they built the cable. Actually, what killed this, do you know what killed this? It wasn't the fact they built the cable. That didn't happen until 2009. This is 2001. I don't know if you remember history, but 2002 we had an election. And we went from an NDP government to a Liberal government, and the view on independent power production and who should do it and at what rate and what we should pay and how much you and I should be exposed to increases in costs, all of that changed on a dime. And this thing went, right? And it was never heard from again. And do you know the company that we had picked, because they got to the point of signing an agreement, do you know the company that we had picked to run this project? It was Ocean Links. They were called Energy Tech at the time. Ocean Links was a rebrand that came later. So the world is very small, and we were at the pinnacle of it for a little while there. So it's probably a good point to break. So come back. We've talked about what's been going on, and I'll come back to you, Vic. I'm going to get local. Going to get myopic. What do we do? I've hopefully explained why modeling and simulation and doing stuff predictively is important. So I said before we're a wave-to-wire modeling study. That's a term in the wave industry, using computer simulation to simulate everything from the wave to the machine to the electricity in the wire. Avoid what happened to Ocean Links. We're a wave-to-wire to washing machine study, right? So we go all the way to the electricity's in the wire, and could you use it? Could it run the fridge? Could it run the washing machine? And we do all that using models. So what we see here, we got a model of the coastline modeling the waves. We got buoys out there, and then we simulate converters in those waves. I'll quickly mention this. How many people have heard of technology readiness level, or TRL? It was I think it originated with NASA. I think is where it started, wasn't it? Was it NASA? Yeah. So technology readiness levels on a 1 to 9 scale. It's at the bottom, and each number has like a phrase. Like 1, you have an idea. 2, you drew your idea on a piece of paper. 3, you made the ideas. And then 9 would be its function in the world and it's designed and it's commercial. The wave energy community they would start here with an invention. This corner up here is what you call commercial. So you're ready, but then this is performance level. And this is something the wave energy community kind of started proposing. Because companies came in here with an invention, they got a supply chain, they learned how to build it, and they would get over here, but the performance sucked. And now to change the performance, you have this great big supply chain, you have all these contractors and agreements. You got to undo everything to change this big machine. And so it costs a lot of money to move from here to here. But if you work with someone like us, when you have an idea and we simulate everything and we change anything we want at a moment's notice, we go from here and we move up, and then we lock in on a concept, and then they start to learn how to build it, and you exit this grid at commercial stage. So our job is to take concepts here, put a hot air balloon under them, get them up on this grid, and then let them go do their supply chain and their manufacturing. So this is the model we run. I'm not going to go into the code. Every dot in there, we track wave spectra. We track a directional wave spectra. You now know what that is at every node. There's 190,000 grid nodes. That's the domain we work in. We're actually well beyond that, but this is the grid that we have running. So we run that model in a forecast and a hindcast mode, and we've used it to generate wave data going back to 2001. And you feed it by knowing deep wave conditions, which we can get from some partners we have in the European Union. And we resolve it hourly. That's near Ucluelet. That gives you an idea of what the model does. So this gives us full spectra. These are the buoys we have out there. This is a Watchmate buoy. It's a 2-meter ODAS platform. There's a tri-axis. It's a 1 meter. Nothing fancy about it. You wrestle it over the rail and you wrestle it back in. And we do that using boats out of Ucluelet, Tofino, and Port Hardy. We're buying one of these. This is an Ocean Flydar. That's a 6-meter platform. It's a $1.4 million piece of equipment. That one also profiles winds. So Curran talked to you about wind. He talked to you about offshore wind. There is a dearth of information on the wind profiles from 0-meter elevation to 200-meter elevation out in the ocean. And so that device fixes that problem. It profiles the wind offshore. So we use these measurements to validate the SWAN model. Sydney. Yeah, local. Buy local, yeah. We buy a lot of them. Not because they break down. I meant that in a good way. That sounds bad. So when you have a model and it's validated, we can do different things with it. What you're looking at, I'll just focus on the yellow. Like we take the raw resource and we apply some technology knowledge to it and we screen it a bit. So we take what's gross and we kind of strip out parts that we don't think technology can get at. We change the estimates. And the yellow is basically showing you the top 10% of all sites on the west coast of Vancouver Island, once we account for what we think technology will do. There's kind of 3 zones that we think to a future industry. There's North Island, Mid Island, and South Island we don't have a lot. Just to show you the numbers here, if we look at, it's the bottom row I want to look at, because this is kind of when you get down to what can technology get out. These are annual averages. So North Island, 14 kilowatts a meter. Mid Island 14.38, South Island 14.04. That's average over a year, but it oscillates wildly. Like in the winter, you can get up over 300 kilowatts a meter, right? So these are just straight annual averages. The reason you don't see anything South Island is that that's the economic value of fishing, and yellow is intense, right? And so when we come in and we work with BC Hydro and the Ministry of Energy, we try and resolve strategic locations. So we take where the resource is good, and then we say, where are other people using the ocean? And let's not go there if we can avoid it. So we get different perspectives, perspective on the left, perspective on the right. We try and blend them mathematically. And then you start popping out pockets where the resource is good and not many people are doing anything there. And those are the bubbles that you see there. The colors are telling you the magnitude of the wave resource again, right? So red is hot, blue is cold. The numbers on the left, these are just ballparks. This is back of the envelope engineering work. If you look at the energy, not power going through, but the energy in those spots over the course of a year, the waves are giving you about 28,000 gigawatt hours inside those little bubbles collectively. If you look at what technology could get at, it doesn't mean you're going to get all of it, because wave energy converters are like, if they're 20% efficient on average, you are world class. Right? That's a world class efficiency on a wave energy converter. But things will change. This is what we think you could go get. So this is the number you would hit with an efficiency to see what you would do. This is the demand on Vancouver Island. So it looks like a small set of regions, but in our view, those are good spots to get an industry going. We wanted to get away from this. So the map you saw is the opposite of this. This is what you saw in 2000, circa 2000. The OES, which is a big agency inside a bigger agency, the International Energy Agency, said that the wave resource has 29,500 terawatt hours a year. That's meaningless. Like across the Pacific Ocean? Like we're gonna go 500 miles offshore to get this stuff? It means nothing. Locally, it's irrelevant. And when you had statements like that, that equates to a herd of zebras. And do you know why zebras pack together, or why they have stripes and pack together? It's a protection mechanism, right? So a lioness, who does all the work while the lion is sleeping, looks at the herd of zebras and cannot resolve the haunch of one zebra. They just see a pattern, and they are frozen. They are paralyzed by opportunity. It's right there in front of me, and I can't seize on it because I can't pick a spot. And that's what happened to wave energy. It is very hard to pick a spot when you can't say what spot is bad or good. Because if you pick a spot, somebody says, no, that spot is good for me, move on. And what do you say in return? Okay, I have no preference, I'll move on. And you just keep moving on. So precision constraints are good things. So once we have the resource in those sites, what do we do with the simulation? So you have a model grid. This is a resource histogram. It's basically just a chart showing you the number of times you get wave, height, and period combinations. So for every cell that you see a non-white color, it means that that period, energy period, and wave height existed. For every one of those cells, we come over and we run simulations of a converter. And over here is a performance matrix. So the cells in this matrix correspond to the cells in that big square grid. And inside each of those grids, cells, we need to run hundreds of simulations, right? We need to seed the waves a little bit differently each time, but they all correspond to that measured condition, and we build that matrix. If you take that matrix, and you take it and you slam it on top of the resource one, and then you track the conditions hour to hour, what you build is a plot like this. So there's 3 different versions here, but we'll focus on the yellow one. It's a trace hour by hour of what we believe the converter is pumping out in terms of power. And the area underneath that curve equals money. That would be energy, and there would be a market price for that. So that's how, this is just for January, we do that for a decade, to see how much energy and how much revenue could come in from the machine. So we do all that in simulation. I talked about John's Valley of Death. Sorry, John. This is just one converter we work with, and the only reason I'm seizing on this one is because it doesn't belong to anybody. It's an academic idea. You can see the masses there. It's fairly big. This is its frequency response. So these are regular waves, and if you put that converter in the water and you hit it with a regular wave of 4 seconds and then 6 seconds, and these are just a moderate height wave, we're not changing the height, you see how the power output starts to go up because this system starts to resonate. It starts to operate at a frequency that it really wants to bounce at. Bouncing buoys with bobbing insides. It's bouncing away, and then the Valley of Death. What happened? It just shut down. It was doing great, right? This is technical. This is not to do with finances or anything like that. You can see where it should be doing well. So this is a device like that. I'm gonna leave it loud because you're gonna hear my PhD student talking. Do you see it bobbing? You see the 2 pieces, the red piece is moving. Do you see a working stroke there? It's kind of oscillating. You see the cylinder moving relative to that inner part. The waves are coming bottom right to top left.
So I got some pitch now.
And watch what happens.
Still low to. Now can you see why I made those overtopping collars?
Notice anything odd? Look at how much movement we get between the red surface and that top surface as soon as it starts going side to side. What, you noticed it, right? It died. Yeah, it died.
You set the damping appropriately, eh? Good. What damping level are we at?
All right. So, okay. That's called walking. And mathematically it's called parametric excitation. So a wave can be coming this way, and that device will be going up and down, and all of a sudden it'll get a little impulse, gust of wind, touch of a finger, and it starts to rock, and it walks in a figure 8. And as soon as it starts doing that, the relative travel is gone and we lose power. So the way to get around that, one thing that researchers do, this is an example of our group, is we run lots of simulations, and we don't change the converter, we change the mooring. We change where the mooring attaches, we change the weight of the mooring. And this is an optimization. Every one of those markers is a different mooring design. And we run this for weeks. The computer does all the work. And it's just ordered. The vertical scale is goodness. It's basically a measure of power. And so you can see, the legend tells you purple was our first generation of attempts, red was a later generation, blue was later, and then the black is last. And you can see how the generations start to move up that curve. And we do quite a bit better. We go from a 60 kilowatt average power to 82. And this is if you're looking from the sky, and if you put a blue marker on the tip of that middle piece, if you were looking above that test, if you were to watch that blue marker, it traces out that blue path. That's that figure 8 walking pattern that you saw. And on every cycle, the figure 8 kind of changes orientation. It's like those things you, what is it, calligraphy? No, I can't remember what it's called, spin the pen around. What was it called? Yeah, something like that, yeah. So when you change, that's the no mooring. That's what the tank was. There was no mooring on that device in the tank. But when we put a mooring on it in simulation, the tip only rocks back and forth. The walking doesn't occur. The mooring shuts it down, and the power production fills back in. You can't learn that from trial and error in the field. So, all right. Put numbers in. This is Hesqui at Sound. This is an integration project. So we were looking at adding 100 kilowatts of wave into a community that's putting a 350 kilowatt micro hydro plant in. This is off grid. Hot Springs Cove is about 40 kilometers north of Tofino. Has anybody been to the provincial park? That has a couple. It's a beautiful place. They are reliant on diesel. They have 6 shipments of diesel that come in a year on barge. There's 3 fuel trucks that roll onto a barge. It's pulled in, which is not a nice trip. It docks on a rough shoreline, they drive down a rough gravel road, and hopefully they offload the diesel without impact. We don't count any financial penalty on environmental risk when we do our work, just costs. If we included environmental risk as a dollar figure for cleanup, things would look a lot better. So we're looking to see what Wave can do in that community. That's basically showing you the community demand in the blue bars. The purple curve is the temperature, and you can see how in the summer, this is a winter-dominated heating load. Okay, so the energy demand is in the winter, beginning and end of the year. The converter is a 100 kilowatt. This is surf power. Unfortunately, another company that did not cross the valley of death. We worked with them for a period of time. It was not our fault. And we built performance matrices for this device. So we know what this device does in different wave conditions, and we can build annual energy production profiles like I showed you for it. That's its performance matrix. Again, every one of those cells, in this case, was several dozen simulation runs. Basically, if we know the energy period and the wave height, for an hour, we go into the chart, we know the power that comes off the device. We've done it predictively. The community's looking, they have a 100 kilowatt diesel, a 250 kilowatt diesel. They have the hydro, the wave. They're also looking at solar. They've got 200 kilowatt hours of storage, and then they've got some demand side management, which is the people. They were looking at load shifting, like not letting hot water tanks heat if the energy demand was already peaking, like just waiting to do that so you could shift your demand around. So there's all these levers, to pull with to see how good they can do in their system. They burn 300,000 liters of diesel a year. So the idea was to see what can Wave do, what's their role. So we do break-even analyses. So the business as usual, which is diesel only, is on the left. There's lots of scenarios in here. I didn't know which ones to pick. Like, do we use the battery and the diesel and the solar? Do we use the diesel and the solar? Do you go diesel wave? Do you do diesel wave battery? Do you do some demand side management and solar and battery and diesel? Do you shut off the 250 diesel? Do you shut off the 100 diesel? All of these choices are a scenario, and we try and look at them all and then cross compare and see where the wave might fit in. So what you're looking at, that's the business as usual. This is over 25 years. It's $35 million to run that plant, and that's largely public money. That has to come from INAC, which I think is still called INAC. If you bring in hydro, what we do is when we bring in a new renewable, we don't charge it. We say, no, the CapEx and the OpEx is free, because we want to expose how we can bring the operating cost of the diesel down. That tells us an avoided cost, and that number right there, that 19 million, is an allowance on what you have to spend on the hydro plant present day. So then we stage it, so we say we bring in the hydro, let's keep the hydro, bring in some wave, bring in some storage. And these little guys are the next little increments, the drops from the business as usual case, and these are additional avoided costs in this scenario that add to here, and now we can start to look at allowances for the wave. So depending on what you bring in what order, we can expose a capital allowance for the wave energy converter and see if that's going to be of use. Just to show you here in these communities, that diesel system in our calculations, and this includes refurbishing the diesels because they actually ran too long, it's $1.50 a kilowatt hour. So that is like 10 times plus what you pay. Like, these communities are in a state of energy poverty. And that's not a comment on their abilities, that's just the logistics. If you bring in a hydro system, again, all the renewables are free. You're trying to expose how you can drop that price down so you can see what you have to work with to break even. The point here is that if you brought in wave instead of the micro hydro, and this is a 100 kilowatt wave converter, that's a 350 kilowatt hydro plant, you can actually get the levelized cost of energy lower with the wave. And that's because in the summer the waves are still there, and the creek they use for the micro hydro, there is not enough flow. And so the energy can't penetrate into the summer, and they have to run the diesels. And when they run the diesels, they have a great big diesel there that's running at low capacity, and it is barfing emissions because it's running very inefficiently. These are all the nuances of an energy system with all these different supplies in play that you're trying to cajole and spit out a good levelized cost of energy. And then the best one we looked at, hydro with the diesel, with the wave, with the battery, with the demand side management, we could get it down maybe to 45 cents a kilowatt hour. And that doesn't mean that's what it costs. It means that when we bring in all the capital expenses of doing those things, we've got an interval between that number and that number to work with before this is like not even worth trying, okay? The emissions are not valued because when you deal or work with Indigenous communities, they don't pay carbon tax. So we don't value emissions. I'm going to leave that one there. What I wanted to show you was just, this is the dispatch in that community when we have 100 kilowatts of wave, there's no battery, and there's micro hydro. What I want you to focus on is these are the diesel generators down here in the capacity factor. And in the winter, you can see how the big diesel in that community, when we use wave, and this is just wave by itself, no batteries, we can shut the diesel off. And that's a really big deal in the community. I can't tell you, like, I've been there, I've sat in the community hall meetings, how badly people don't like the noise and pollution that comes off those generators. It is a cultural affront. It is a real stick in the gut, and they want to get away from it in a very, very bad way. And then in the summer, that big diesel turned on for 1 hour. We couldn't quite squeeze out entirely. So the main thing is that wave allows us to get out from under the diesel. This is a decision diagram. So this is how we take all these results. The community is starting with a micro hydro diesel system right now. What this chart is this is a decision matrix. So the first choice they have here is that they can implement wave. And I've chosen to look at this from a liters of diesel mitigation. So if they choose to add the wave system in, they'll drop 40,641 liters of diesel a year. If they choose to change their energy consumption behaviors or save energy, this is re-insulating windows and doors and changing to vinyl instead of single pane glass, redoing the insulation in the roofs. They'll cut their demand down, and that'll save them 27,000 liters of diesel. So if you choose to go this way, your next choice is, okay, do I now implement the energy savings, or do I maybe add 200 kilowatts, or do I jump the 200 kilowatts and add 500 kilowatts of storage? So these are the types of matrices we want to generate, so planners can look at this and say, okay, on every increment, we build our system with the capital we have every year from the federal government. How are we going to do this? The optimal system in this case was 500 kilowatts hours of storage, energy savings, and then the wave. So how do you get from here to here? You plan your route to get there. The end point in the end is the same, but how do you want to get there over a 10-year period? We're almost there. I had a question on cost. So for this scenario, this run, and these things are really sensitive to fuel price escalation, to discount rate, to inflation, a lot of things I don't know as much about as I should. How does wave look on costs? So from these numbers, if you look at what our wave energy plant saved the community and the energy it pumped out, it basically needs to operate at a levelized cost of energy of $380 a megawatt hour. If it can do that, that's an indicator. If you could find a company that can do that, that's an indicator it's going to be good in this project. It will not cost the community more money, and we will get the diesel mitigation, and we will save the pollution and the noise. We need to build it, or to be able to build this thing for another way of looking at it is $46,000 per kilowatt. Sometimes people price converters on a capacity. So $46,000 per kilowatt is what we need to do. All right, this is the best thing I have for you. This is, and it's not great, this is a survey of international reports on the cost of wave energy converters, because I knew somebody would want to know about costs. So we're working on small scale wave. This is 2020. As you move to the right, this is 2050. And they're looking at 5-year increments, and they're applying learning rates that they're getting from analogy to solar and wind. They're looking at reported costs of wave energy converters. And what they're saying internationally is that converters right now operate at, this is like 1,200, let's say, what are we, 13? This is like $1,250 per megawatt hour. We need the system to run at $380 per megawatt hour in order for it to make sense. They're suggesting that through learning and experience that by 2050 we can get down to, let's say, $550 per megawatt hour. The red line is where we need to be. I will tell you now that that gray curve is a load of hokum, because I think it's based on 3 reported examples that have existed in the world. And we have been deploying converters since about 2012, 2015 at some of those test sites I showed you. And what they report as an operating cost, if they have a massive failure and incur an operating cost because their technology readiness was good but their performance level was garbage, all of these things contribute to these projections. The sample size is too small. Needless to say, there's still a challenge ahead of us. It's not a cost-effective way of generating power based on what's available to you now. Okay. I'm going to just, closing off, last 2 minutes, why communities? We have results looking at integration into the grid, but I'm a firm believer in the remote community market. One, it's a high cost of energy right now. I told you before, our estimate is that real world costs, they're paying about $1.50 per kilowatt hour. Those red dots are all off-grid communities. There's over 50 of them in BC. There's around 300 in Canada. Red means diesel. The other dots mean off-grid, but green means biomass, blue means micro-hydro, stuff like that. The red ones are the evil ones. That's the one everybody wants to get rid of. So provincially, federally, everybody wants those things switched over. In the community, they want it switched over. And BC First Nations, the red dots in the middle of the province have been amazingly productive with clean energy projects. So there are 78 projects in Indigenous communities with over 1.8 gigawatts of installed capacity. That's a huge number, right? Our capacity province-wide at our generating stations is like 9 or 10 gigawatts. So they're like 20% of what we do as a province. It's largely micro-hydro. The problem for the communities on the coast is they can't use microhydro. Hot Springs Cove is one of the few that can. They have a creek with a significant water flow. But for them, it's tides, it's offshore winds, and it's wave. They need those technologies to follow their colleagues in the interior Indigenous communities to do these clean energy projects. And they are trying to move that way furiously. And so it's my belief in BC that it's Indigenous communities that will take the lead. To be frank, we could go out in the street and you could ask any person you walk up to how proud they are that BC's grid is 98% green. And they'll say, I don't care. I care that I pay 10 cents a kilowatt hour, right? That's what I care about. And people will not tolerate changing that price. You can listen to a news report when we had Site C going in, right? We have like a modicum increase on your rate and the world is ending. The world already ended in a lot of these Indigenous communities and now they're resurging, they're coming back. They're not bothered by a financial investment or a little technical risk. And so for wave energy to compete, it needs to break in, it needs a track record. We need to have more than 3 samples that make up that LCOE curve I showed you. And the communities that will do it, I guarantee you, will be Indigenous. That is the way it will work. They will go from being at the tail end in terms of technology, and they will leapfrog to the front, and the rest of us in mainstream society will go, oh, well, look at that. It can be done. And then we will adopt, right? And then we will invest. And the International Energy Agency is saying the same thing worldwide. So I'll leave you with this. You know, we could do all these remote communities and we could get rid of all the diesel. In BC, our problem in BC, you're going to learn about this in a few weeks, is we're trying to find 6.1 megatons of emissions. We have a plan to 2030 to get our emissions down, but we have a 6.1 megaton gap. We do not know how to cover it by 2030. From 2030 to 2050, there's another 25 megatons of emissions we're trying to get out, and we can't figure out how to cover that yet. How much diesel, if you wanted to get rid of those just by getting rid of diesel, you'd have to get rid of 2.3 billion liters of diesel a year. Hot Springs Cove consumed 300,000 liters of diesel a year. And you could say, well, what is the point, like from a clean BC perspective, of getting rid of diesel? It's not about BC. Like, I get really pissed off when people say, why is Canada even bothering? Our footprint is so small. There's an entire planet, and I think the last 4 years have shown that there's always the risk of a dearth of leadership in these areas. Just when you think somebody's leading and gonna pull the bus, they get off, and somebody's gotta step into the driver's seat. And Canada's in a position to do that. There are 3,000 off-grid communities in Chile, sitting on a coastline at low latitude, exposed to a wave resource. And if you do something here, working with our Indigenous peoples and their ambition and their motivation, and then you export that idea into a country like Chile, now you have Hot Springs Cove, all of our 30-ish coastal communities, and 3,000 more. And then you go to Indonesia, and then you go to Southeast Asia, and then you move on. So that's what this is all about. It's about taking these little corners of the world, these pockets that are energy poor, and as the image at the bottom shows, it's about leapfrogging at small scale. So anyway, that's all I have for you. And when you've been lecturing for 15 years, what you realize is you take the time, you consume it totally, and then nobody can challenge you because we're all going to leave in 20 minutes. Right?
Well, thank you for a great perspective, and I think it fits the series very well. And I'm sure there are a lot of questions. We're open to questions at this time.
Here and then here? Yep.
Thank you.
Yep.
The point absorbers, I just want to check for clarification. There are moored ones and there are unmoored ones. Is that correct?
They're all moored in the end. They have to be. But the funny thing is that when point absorbers have been designed, nobody wants to consider the mooring because it's a very, very messy engineering problem. It's highly nonlinear. Moorings they have a geometric stiffness. So if you have something moored and you have the cables there and it sits there and you know how it pulls the body back, if you have a wind on the surface hitting the device, you have a current coming from here, and we have our waves coming from here, the whole thing inevitably will shift. And the mooring will change configuration. And as soon as it changes configuration, what it does to the converter is now different. And so the multitude of conditions and cases we got to look at, it literally just becomes so overwhelming that before we had computer simulations and we were doing things on pen and paper and literally old sea dog tricks, and I'm not making that phrase up, that phrase exists. That's how moorings were done, by old sea dog tricks. People just didn't want to touch it. So now we're at a point where we can do, like I talked about with the optimization, and look at what the mooring design should be. When I mentioned that in the tank the device was not moored, it's because moorings don't scale into test tank. They're a drag-dominated hydrodynamic, so you have to Reynolds scale them, but you scale the converter differently because the forces that you're experimenting with are different, and the two scalings do not work. You'd have to take the mooring lines in a test tank would have to be like fishing line filament, but they're too light. So the weight doesn't scale right, the drag doesn't scale right, and so we typically don't do it. Does that make sense? But in reality, it has to be moored, otherwise it will bye-bye. It'll go away, so, yeah. One here, and then I'll come there, yeah.
So what happens if you take the snake
Yeah.
and you suspend underneath it oyster cages, oysters growing cages?
Yeah.
First of all, would it dampen the effect? And if it didn't, maybe you could sell that as an add-on to the First Nations.
Yeah, okay, so what we're talking about is almost like a cogen opportunity. So let's talk about the cooperative opportunity. Where that exists in the industry is that floating offshore wind turbines, which Kern gave you a picture of, they tend to want to stay stable. They don't really want to rock because it makes it harder to control the rotor. So they insert shock absorbers, they're heave compensation devices inside the structure of the platform. They're like little bouncing masses inside the converter that make the platform stop moving. That's a wave energy converter. It's a wave energy converter operating in a shutdown mode. So wave energy and wind energy have come together in that space. They're complementary. Aquaculture and the energy production would only be complementary in the sense that the aquaculture provides a market. So they need energy to service those things, manipulate those farms, feed fish if it's a finfish aquaculture site instead of shellfish. But as soon as you put an organism on a machine and it grows, what you're basically doing is taking the skin of the PLEMS converter, even though this stuff is hanging off. It's the equivalent of growing like some kind of, you're changing the hydrodynamic properties of the system, And it's changing as the stuff grows. And the mechanical engineer charged with running the device would be like, are you crazy? Like, because we just designed the whole thing to generate power, and then a month later it's not doing anything because it's totally hydrodynamically just a monkey wrench into the gears. So does that make sense? Yeah.
Just before you do that, I might just add that I first got interested in this whole offshore wave energy generation possibility by being involved in the oil industry, and we had the offshore drilling platforms. And there the idea was to minimize heave and stop the motion, and I always felt there was a bit of a synergy there, and so I left the oil industry and joined Brad.
You know where you are right now, right?
Sorry?
You said oil and gas, you said offshore platform, you said drill.
Oh,
You
yeah,
say
no,
pipeline,
those
you're going to
are
cover
all-
off
those are bad words.
revolver.
Anyway, more questions.
Yeah.
You're a mechanical engineer.
Yeah.
And I know you've gone into the modelling side.
Yeah.
But what's always interested me about offshore wave energy is the enormity of the structures.
Yeah.
And you've got to put a structure there that will withstand the worst waves, right? We don't know what those are.
Yep.
But also you've got the ongoing problem of maintenance.
Yep.
And you've got a huge structure offshore that's deteriorated in a terrible environment,
Yep.
it's salty, it's just the very
Yep.
worst for mechanical things that move.
Yep.
How have you dealt, do you deal with that? I mean, in your costing, have you looked at the maintenance of these things? I mean, is that?
Yeah, that's a great question. So where you would rip that techno-economic bit that I gave you a little snapshot of, you know, try like avoided costs, renewables come in for free, right? So that you look to see, you know, what kind of diesel you can mitigate and then what your allowance is. And I showed you that pricing curve where my colleague, it was a colleague of mine that wrote that. Don't tell her I said that was Buckham, the thing anyway. So she started with levelized cost $1,250 per megawatt hour, right? That comes from a couple of examples where short-term deployments, they had converters out for a couple of years. Obviously something happened. There was a big expense to fix it or move it. And in a small sample size and a short time duration, that OPEX, like even though it's over 3 years, that's nothing in comparison to a 20-year lifetime, right? So that happened. There was if we had 20 years of operation and that happened once, we take the 20 years, we bring it to present day to get a levelized cost of energy, it wouldn't look that bad. But it's a 3-year project with a 3-year, you know, full view, it's horrible. And so that learning has got to go on, but we somehow have to take a view where we don't let that learning on how we solve those things, you know, stop the problem. What's happening, those tasks are very similar to offshore oil and gas. Very similar to if you were to look at floating tidal turbines. Do you have a tidal talk?
No, we haven't.
Yeah, well. So floating tidal turbines, there's been some, like Orbital Marine Power has had something deployed for 3 years, and they've actually, it's not like they're intentionally breaking it, but they're waiting, they want stuff to happen. Even if they don't need to, they'll go out and do these service trips just for practice, right? It's just a fire drill. And they chart their costs and their time to do it, and they've been trying to prove. It's a very innovative way of doing it, rather than show there are no problems. Like, hey, when there is a problem, this is how it will. So there are established practices, you know, in offshore oil and gas. I'm confident in terms of materials that we can get around that. It's just a question of developing the skills and the assets. There are techniques with some converters to avoid the high energy sea states. Some devices are made to porpoise. So they'll take, you know, the bobber on a string pulling on a pump. They'll ratchet that thing down, and if it's a 100-meter wavelength, how deep do you have to go to get out of the wave? 50 meters. So they'll pull it down 50 meters and they'll ride it out, and then they'll come back up. So that's called porpoising. And same thing for offshore wind. Like wave will compete with offshore wind, and it'll compete in terms of the OPEX because some of the OPEX concerns are the exact same, right? Same concerns, offshore, harsh environment, how do you get to it, how do you service it? Whichever one goes first, hopefully the other one, well, offshore wind will go first, who are we kidding? Hopefully wave can benefit from. So.
Yeah. Do you want to mention tidal energy just briefly?
Oh, yeah. I mean, you can go look at something called FORCE, F-O-R-C-E. It's a nice little acronym. It means Fundy Ocean Research Center for Energy. And so there was a large turbine, 2 megawatt capacity, tidal turbine, not a wave energy converter, was put down on the bottom of the Bay of Fundy as part of the FORCE program. And so you can see images of some of the supply vessels that were designed to get that thing out there, lower it down into the water. Different problem, it's fixed on the seabed, it's a turbine, it rotates. That company, like I really got to say, like corporate morals, like corporations being global citizens, we got issues. The company that did this was Cape Sharp Tidal, because you're talking about how do we learn, like how do we solve this? So they develop all this infrastructure. Cape Sharp Tidal does. It was a joint venture of Emera was the Canadian utility, Open Hydro was the tidal turbine developer, and then there was a French naval engineering giant that was the big fish that was part of the. So they get this thing out there, they build a great big barge, they lower it down, and the French company pulled the plug. We're done. No more. We're not getting, there's no return. There was political noise about the feed-in tariff in Nova Scotia that was going to provide them 56 to 60 cents a kilowatt hour, was not going to have political momentum. It wasn't going to make it through the next election. They're like, we're going to lose that. We're going to be off grid. They pulled the plug. They pulled the plug when the device was on the bottom. And it's still on the bottom. And so the province of Nova Scotia, which subsidizes the operations at Force, it's a test center. It's like those leased berths I was showing you for Wave. Same thing. So they have a call for proposals out, and they're looking for companies to come in and take the berth at a discount, sweetheart of a deal on the lease costs on the berth, and you can come develop your turbine and put it here, and you can grid connect it because we've paid for all the cable. But you got to get this thing off the bottom to get the deal. So, what's that?
It's under 60 to Buckham now.
Yeah, they're rocky. So they have pebbles the size of that move around down there, and so yeah, they don't have mud, but they have something even worse. So yeah,
it's very site specific. I mean, tidal energy. There's only a few locations in Canadian waters where there's sufficient force to be able to capture that energy using a turbine. Seymour Narrows is one. Bay of Fundy is another. There's probably a couple more, but not big numbers.
Yeah.
What are the impacts on marine life? Because those things can get pretty noisy and whales need.
Yep. So the whale one comes up a lot. So the leading authority on that is a lady named Andrea Copping, who's with Pacific Northwest National Lab. She's at Squim Bay, which is just where north. It's Olympic Peninsula. It's just to the east of Port Angeles. Yeah, just to the east. So you can take the Coho over, you can drive half an hour, and you can end up at the PNNL lab in Squim Bay. And they develop monitoring technologies, so both visual and acoustic, that could be deployed if they have a power source or powerful enough batteries. And they would sit beside a converter and watch. And what agencies like DFO in Canada, in the US, it's NOAA, what they are asking for is they want visual or acoustic, like underwater sound is like your eyes, right? They want visual proof that there's no strikes, right? And in Canada, the Fisheries Act changed in 2018 or 19, and we have Bill C-69, which is changing the rules of the Environmental Assessment Act. And so what we're down to now is there's, I'll say, a threat that we're looking at death of fish on an individual scale.
Pardon?
Death of fish on an individual scale is a criterion with DFO. So if we have one salmon, then that means it's possible. And I don't, as an engineer, I don't agree with that. Because the death of fish criterion, meaning that you can't approve something if it's going to cause death of fish, and I'm saying that death of fish means that if it's 1, it's greater than 0, there's death of fish. The death of fish criterion applies to all industries proposed or existing in the ocean except for 1. And do you know what the 1 is? Fishing. So that is just historical norms. That's not logical, right? That's saying that the fishing, it's not about death of fish, it's about value, right? And we look at what we do with our fishing industry and how we manage it. Have we allowed value to be eroded a little bit? I think you'd have to say the answer is yes. And now you're going to tell me that we can't possibly even erode that value a little bit to the benefit of so many other causes by doing this. And that's my concern in terms of permitting. So there is nothing in the world at this point that says mammal strikes are going to occur. And there has been observations done. You can look up a device called PLAT-I, PLAT-I. It's a tidal turbine operating in the Grand Passage near the Digby Gut in South Nova Scotia. And they have video feed. And I'll use tidal turbines as an example, because if you watch a tidal turbine, you now know what they look like, but if I was the rotor, I'm 3-bladed, right? Okay, 3 blades. They basically rotate at that speed. That's how fast we're going. It's not a squirrel cage fan in your fireplace spitting out air. We're very slow. Wave energy converters oscillate on a few meters every 10 to 13 seconds. So we're talking about me walking over that wall and back here in a 13-second gap. That's how fast the apparatus is moving. So people have been looking at this, and they've been finding that fish strikes and mammal strikes are just not a thing. But in Canada, they say that it doesn't matter if it's been proven in Denmark. Denmark is not Canada, and I must have that video evidence from Canada. So that's what the sector's up against. Yeah.
Time for one more question?
Yeah, sure. I can do more.
Well,
you gotta go. Yeah.
Last week with wind, we learned that size matters.
Yeah.
And I'm wondering if that's the same thing with hydro?
With wave?
Power, the bigger the thing, you get the multiple advantages that you do?
Yeah, there is a bit of a limit. So if you look at point absorbers are called that because when you look at from the sky, they look like a point. And they're based on the idea the water level is going to go up and down uniformly around the device. So if the point absorber diameter starts to get to a point where that wavelength, which is how long?
13 meters.
100 meters, let's say, right? 50 meters for below water. You got it right on the other question. But so if that 100 meters, that's a peak, a trough, and a peak. That's 100 meters. So if you start taking something and you put it on that peak, and it's now like 50 meters in radius, right? All of a sudden, the water level around this thing is not uniform anymore. You're starting to bridge wavelengths. So there's a physical limit to how big the point absorber could go, and there's other limits for other technologies.
And how about corrosion?
So, like anything in the ocean.
How do you, what's the maintenance level?
Anything in the ocean is a problem. It's not a problem. Hydraulics are nice because they're pressurized to hold the hydraulic fluid in, so they're water sealed at high pressure. They'll hold water out. And when you have strokes of a hydraulic interface, right, every time you go up and down, anything that was there is cleaned off at a microbial level now, right? If that's the right word, I'm not a biologist. Before it becomes a crustacean. The parts of the travel in that hydraulic cylinder that don't often get hit, right, those could start to form different growths. And if those ones get encrusted and then you get a large travel event, you come down, now you have a problem. Which is why, by the way, you should always drive your car over speed bumps. Do not drive around the speed bump. Get the suspension to travel so that everything stays lubricated and working properly. So, yeah. Can I do one more? He was very patient.
Okay. Can you talk about the role of BC Hydro in either, helping, getting away, bad policy, good policy?
Yeah, okay, so let's just say the BC context. So BC Hydro has not been in the business of new forms of energy generation since 2002. That was when that demo shut down. They're still not. They view wave as being something that they need to put on their radar. So one of my projects is supposed to feed them information that goes into something they call the Resource Options Report. And that's the document that they build a battle plan for, which is called the IEP. That's where the rubber hits the road, is the IEP. So they're not really interested in hearing much more other than where is it? Like how far would it be to get to it? How do we have to change transmission infrastructure in Vancouver Island if we brought 500 megawatts ashore? So that's where they're interested. Now, the BC Utilities Commission is going through a review of a concept called the Indigenous Utility. And so they're looking at a designation of an Indigenous utility. What does it mean to be an Indigenous utility? What's the ownership model? What technologies can they decide to implement as an Indigenous utility? And how would that Indigenous utility sell power back into the BC grid? That is the discussion that's relevant to wave energy. Because BC Hydro will be a follower, which is totally ironic. Like, it's perfectly positioned to be a leader, it will be a follower. Yeah.
And that's because of the policy they've been directed
Yeah.
to do, as opposed
Yeah.
to becoming an energy.
Yeah. Yeah.
Either a dam.
Yeah. Yeah. And they trade power across the border, right? And for them to have an intermittent renewable come on stream, which is then screwing up their trading of power back and forth with Washington, is difficult. It's hard. So, yeah.
Well, thank you, Brad. Thank you on behalf of